thanks for watching, and today let's revisit the method of characteristics because I want to give you an even better way of solving first order PDEs. In particular, let's try to solve ut plus x squared ux equals 0 with initial condition f of x. Previously, the way we solved it was using the slope method, where we said the slope was x squared over 1. The problem with this method is not only is it not rigorous, but also it doesn't always work. The method I'll tell you today will always work and helps us to solve first order PDEs. And what it's called is, it's the method of characteristics. And it starts out by considering really any curve in the xt plane. So consider any curve. We call it x of t comma t in the xt plane. And I want to show you a little picture. So again, this is x and this is time, and we have our curve here. So x of t comma t. And the main question we want to answer is, how does your solution u change as you walk along that curve? So question, how does u change as you walk along the curve? Along the curve. Now, it seems weird to ask that, but we've actually already seen this phenomenon before, because when we did the slope method, we saw that u was constant on parallel lines. So in particular, the value of u did not change along those lines. And we want to see the same phenomenon here. So let me just illustrate. So once again, the phenomenon we've seen before is that we had parallel lines, which are our curves in this case, and we saw that u was constant on each line. For instance, u had value 5 here, maybe you had value -3, or you had value 1. So in particular, let's record those values. So let's call that h of t. So let h of t be what's called u of x of t comma t. It's a bit weird notation, but all this is just the values of u on that curve. Of u on the curve. In fact, I want to illustrate this. So, once again, we have our solution u. We have our curve, x of t comma t. And h of t is just the value of u on that curve. So this is h of t, which is u of x of t comma t. And once again, as you walk along that curve, h of t just tells you what the value of the solution is. And again, our hope is that h is constant on that curve, and in particular, our hope is that h prime is 0 on that curve, and which therefore prompts us to calculate the derivative of h. So go calculate h prime. And in fact, this is what we'll do right now. So now, step 2. So let's do h prime of t, which is really d over dt, h of t. And now remember the definition of h. So that's d over dt, u of x of t, comma t. And since both the inputs depend on t, this prompts us to use the coordinate method. So I want to remind you of the diagram. U depends on x and t, and then x and t depend on t. So using the chain rule diagram, this derivative is just partial u over partial x times dx over dt, and partial u over partial t times dt over dt. So I know it's a lot to say. Partial u over partial x, dx over dt, plus partial u over partial t, dt over dt. Which simplifies, so this is just ux, and then times x prime of t plus ut times 1. Now, very important. So far, what we've said, or so far what we've shown, is true for any function u. And in particular, we have not used the PDE yet. And this is very crucial when you solve the PDEs. At some point, please use the differential equation. If you have a PDE problem and you don't use the PDE, then it's very likely wrong. So now let's do that. So we know that the PDE, I believe, is ut plus x squared ux is 0. And therefore, we can substitute ut. So we get ux times x prime of t. And then I believe minus x squared ux. And I want to remind you, this x here is the curve. And so this thing is really the same as ux times x prime of t minus x of t squared times ux. And now what's nice is we can factor out ux, and we get ux times x prime of t minus x of t squared. So once again, the way the function changes on the curve is precisely this quantity. Now remember, x so far is really any curve. Now here's the upshot. If we choose our curve x such that this quantity is 0, then this is good, because then h prime would be 0 and h would be constant on those curves. So in fact, let's do that right now. So step 3, this is, I would say, the most important part of this problem. So upshot. If we choose x of t such that x prime of t is x of t squared, let me box that, then we would get h prime of t is 0, and therefore u would be constant on the curves. The curve x of t, comma t. So in that case, we would get curves, those curves x of t, comma t, and u would be constant on those curves. Kind of like this and like this. This is an x and t. And for instance, as I said, u might be 5 here, u might be minus 3, etc., etc. And there's some nice terminology associated with this. This ODE for the curves, that's called the characteristic ODE. ODE. And the curve itself is what's called the characteristic curve. So once you solve this ODE, which is easier, you get what's called this characteristic curve, and in this case, U would be constant on those characteristic curves. And you'll see that will help us solve the PDE at the end. So now our next step is really to solve for the curve x of t. So if I'm not mistaken, that is step 4. So solve x prime of t equals x of t squared. So in this case, we have dx over dt is x squared. And we can solve this using separational variables. So the good separational variables from ODEs, not the bad one from PDEs. So let's divide by x squared. So we get dx over x squared equals dt, and then integrate this. Integrate, and then I believe an antiderivative, it's minus 1 over x is t plus some constant. So x, I believe, or in this case x of t is minus 1 over t plus c. But also just beware, we did divide by x here, so we need to check if 0 is a hidden solution, and in fact the 0 function does satisfy this ODE. So it's really x of t equals that, or x of t is 0. And again, that's just a hidden solution. But in practice, we don't have to worry about that if we assume, for instance, that f is not constant. And so let me illustrate this now. So let me draw those curves. So once again, what do those curves look like? So this is an x and t. Remember here, x and t are switched. And so in particular, those curves actually look like this. So x of t is minus 1 over t plus c. And remember, there is a 0 curve here. X of t is 0. And even this is true for negative x. I think it's maybe looks like this. I might be mistaken here. But, so what we get is those are our curves. And once again, the function h is constant. So in other words, u is constant on those curves. So I believe now, I believe that's step 5, either step 4 or step 5. Now, since h is constant, think energy method. The value of h at t is the same thing as the initial value. So h of t is h of 0, because that's one thing we haven't used yet, the initial condition. And then you can use the definition of h to get u of xt, comma t is u of x0, comma 0. Now remember, we know the value of x of t here. So x of t is again minus 1 over t plus c. So what we end up getting is u of minus 1 over t plus c, comma t is u of minus 1 over 0 plus c, comma 0. And it's u of minus 1 over c, 0. And now remember the initial condition. So u of x0 is f of x. So that is f of minus 1 over c. Now we're almost done, because we've shown that u of this gibberish value, comma t, is f of minus 1 over c. But what we want really is u of x, comma t. So essentially what we'll do, we'll let this be equal to x, and we'll solve for minus 1 over c in terms of x. So once again, this is what we had so far, and so now step 6, let x be that value, minus 1 over t plus c, and we want to solve for minus 1 over c in terms of x and t. For minus 1 over c in terms of x and t. Okay, so let's do that. Let's first solve for c. X is minus 1 over t plus c. Well, that gives you, take reciprocals, minus t plus c is 1 over x. So t plus c is minus 1 over x. And so in that case, c, collateral case c, is minus 1 over x minus t, which if you want is minus 1 plus xt over x. And then 1 over c, 1 over c is minus x over 1 plus xt. And so minus 1 over c is x over 1 plus xt. And I promise we're almost done. We just need to substitute into here. So again, I left this here, but the last step, so really the grand conclusion, because now, what is u of xt? Well, remember, x was this gibberish, minus 1 over t plus c, comma t. But now, that is f of minus 1 over c. And then in the last step, so step 6, we found that this is just f of x over 1 plus xt. Which, lo and behold, is our solution to the PDE. And so in particular, if you want, you can check that u solves this PDE, but also more interestingly, if you plug in t equals 0 here, you do end up getting f of x. Last but not least, I just want to tell you a couple of cool applications of this. So, applications. The first one, and that will be part of another video, is we can use the same ideas, if you wish, to actually derive what are called the Navier-Stokes equation. Which are really equations for atmospheric pressure. In other words, those PDEs actually give you the weather, at a certain point and at a certain time, which is really cool. And in particular, the reason it's also very popular right now is because it is one of the 7 millennial problems. So the millennial problems, they're very hard equations or very hard problems, and for each problem you solve, you actually get $1 million. And so if you want to find a nice way of making $7 million, solve all 7 problems. But just beware, it's a little bit hard to do that. So that's the first application. More interestingly, or I guess equally interestingly, because we have those characteristic curves, the problem is the characteristic curves, they may intersect. So the characteristic curves may intersect, which leads to the phenomenon of shocks. So shocking news, and let me illustrate. So suppose you have 2 characteristic curves. One where we say u has value 1, and the other one where u has values -1. And suppose those curves, they clash at the point. Then really the question is, what is the value of u at that point? Is it 1? Is it -1? Well, we technically don't know, at least for now. And the reason this is important is because this happens, for instance, in traffic flow, where you have one car going this direction and another car going that direction, and in particular where they intersect is where the cars crash. And that's why we have this phenomenon of a shock. And in particular, this is related to what's called Berger's equations. Probably the most famous first order PDE equation, which actually models traffic flow. So believe it or not, there is actually a PDE that models congestion in cars, which is really, really cool. All right, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.